So this is the second video for fluids, and my name is Brody Harrison. This is the problem we're going to be solving. I don't know if you can, how well you can see that, but that's the problem. Basically, we have a tank and a pipe coming out of it with a pump, and it's just open to the atmosphere here, full of water, and it's pumping out into the atmosphere, and this is going to go down as it pumps out, obviously. So we're given a couple things here. We're given this height, which is 6 meters, so Z1 equals 6 meters. The diameter of the pipes here is 0.07 meters, so D equals 0.07 meters. The length of this pipe is 2 meters, so L equals 2 meters. We're also given the head gain from the pump in equation form, and that's going to be equal to 20 minus 2,000 Q squared. And what we need to do is determine the volumetric flow of the system, show that the observation that the flow is turbulent is correct, and that if the pump is operating at 70% efficiency, determine how much power must be supplied to the pump. So what we're going to want to do first is take a couple things. I've already done it from the textbook. So the pipes are made out of cast iron, and that will give us an epsilon or roughness factor of 0.00026 meters. And same thing with the loss coefficient. The loss coefficient is going to come in right here when the water is entering the pipe, and that is going to equal 0.5 in this scenario. And both of those are from tables in the textbook. So we know that volumetric flow is Q and is equal to area times velocity. We can do the area pretty quick. Pi over 4 d squared equals pi over 4 squared. And it turns out being 0.00385 meters squared. So that's the area. And we also know that later on we'll need this to prove turbulence. Reynolds number, this equation is rho VD over mu. So the best way to go about this is with the head loss equation, which is technically a form of Bernoulli's equation. So it's going to look like P1 squared over rho G plus V1 squared 2G plus Z1 plus HP equals P2 squared over rho G plus V2 squared over 2G plus Z2 plus HL. And there's, believe it or not, a lot is going to cancel here. We know that this velocity is going to cancel, become 0, because this velocity here, since this is draining, it's draining at essentially negligible speed. It's not going to affect anything, so we're just going to pretend it's 0, and this is going to get canceled out. The pressures also, they're both open to atmosphere, so that cancels out as well. We only have one Z, so this one can get canceled out, and this one will end up being the 6. But say like this is 0.1, 0.2, and this is equal to 0, this is equal to positive 6. And then we're going to have our head gain and head loss. This is from the pump, and this is from everything that slows the water down as it's moving through the system. So the next step is going to be to find out the head gain and head loss equations. So we know that the head gain is going to be this equation here, essentially, right? So 20 minus 2,000 Q2. But since we know that Q squared, but since we know that Q is equal to area times volume, this is going to end up being 20 minus 2,000 times 0.00385 V squared. And we also know that the head loss is going to be the head loss minor plus the head loss major. And each of these equations are going to be hold on a second, V squared over 2G, and then the loss coefficient, plus friction factor, which we're going to find in a second, length over diameter times velocity squared over 2G. So this is our head gain. This is going to be our head loss equation. What we need to do now is find the friction factor. And what you do to do that is you find this ratio here of epsilon over diameter. And this, in this case, is going to equal 0.00026 over 0.07, which is going to equal 0.0038. Oh, sorry. This one is going to equal 0.00371. So what we're going to do with this value here is we're going to take it over to the Moody diagram. So I'm going to try to show it on here. I don't know how well it'll work out, but this is the Moody diagram. What we're going to do is we're going to take our number we got for this ratio over here, and since it's going to be just under 0.004 here, we're going to run this way with it to find our friction factor, and it's safe to say this is going to be about 0.028. So we'll say F is equal to 0.028. Once we have that, we can basically take this, this, and this, and plug it all back into this equation up here, which is going to be now looking like so we pretty much have everything here except the velocity, which is what we're still looking for this equation to find the volumetric flow rate. So using this, once we plug everything in, I'll plug everything in quick. Oh, oops, I forgot a term here. I forgot to bring down this. So this is going to get dropped into here too. So pretend that's here. We'll go to this step. All right, so once it's all plugged in here, we're going to have 6 plus 20 minus 2,000 times 0.00385 V squared equals V squared over 2G plus F times L over D times V squared over 2G plus V squared over 2G times the loss coefficient. So on to the next page. After that, we'll simplify it one more time algebraically. 6 plus 20 minus 15. So then it's going to look like that after one more step of algebraic simplification. Then we're going to solve for v. That's all algebra. I'm going to skip those steps. But v ends up being 0.662 meters per second. And now that we have this, we can solve A, B, and C of our question that's asked. So A is volumetric flow rate. And we know that's area times volume. So if we have an area of 0.00385 meters squared times a velocity of 0.662 meters per second, we have a volumetric flow rate of 0.0025 meters cubed per second. And then that leads us to B, which is it's asking us to verify that it's turbulent. And that can be done with Reynolds number, which we also needed the velocity for, because Reynolds number is equal to rho VD over mu. So this is going to be 1,000 times 0.662 times 0.07 over the mu here is 1.12 times 10 negative 3. Mu is viscosity, rho is density, and then velocity and diameter, just to clarify that. So once we get that, we know that the Reynolds number is equal to 41,375. And this is way bigger than 2,000, which is the standard threshold for turbulence. So anything above 2,000 is considered turbulent flow. Anything below 2,000 is, with a Reynolds number below 2,000, is laminar. So since this is way above, it's definitely turbulent, and that's verified. Lastly, it's asking us for the work required by the pump if it's operating at 70% efficiency. So this formula here is work equals rho GHQ over the efficiency, in this case 0.7 for 70. Here H equals 20 minus 2,000 times 0.034 squared equals this turns out to be like 17.688. So then this is, we have all these values, we just plug it back in. 1,000 times 9.81 times 17.688 times Q, which was 0.0025, all over 0.7. Work equals 619.71 watts. And there you go. That's all the solution to this problem here. And I'll top it off with my signature quick. And today is the 17th. Thank you.